the project where we train the model, we evaluate the results, and of course, we look at the validation. And we also talk about what model interpretability means and why we need it. So if you have not followed up on the last video, you could kindly try to check so you could see why and what this model interpretability is all about. And if you follow us last week, we talked about the global explanation and the local uh, explanation, and then we talk about the post hoc, and then under the post hoc we talk about the model agnostic techniques and the model specific techniques. So we talk about all this last week, and I believe I also shared the material on my GitHub. So if you don't have the slide, you can actually download it to follow it through. So today, looking at what we have done from that last week, like I said, you have to forgive me because no, not have, because I'm not forcing you. So I'm pleading. So please, you should forgive me. Because my week was really crazy with so many schedules. So I didn't really have much time to prepare the slide. So probably I could just talk about a bit, and then next week I could give you more elaborate examples and other things from it. So I wanted to go into the hands-on section on model interpretability in health and medical sciences example. Although from next week I could include examples from other domain, but this will be a more of like a follow-up from our last modeling using the breast cancer. I don't know if you remember the Wilkinson breast cancer dataset, if you remember that. So it's kind of a follow-up from that. So like I said, as we continue to unravel different techniques in machine learning, the complexity increases because some of the models we're using are black box. And because they are black box, we need to understand what is happening behind the hood. So this lack of transparency and also the fact that it's an opaque approach that is very complex for us to understand, it makes us not to want to trust the model. And because of that, if you imagine in field like health sciences that has to do with human life, it would be a very terrible thing if we do not understand what the model is doing. So I talked about a book by Christopher Moller last time on interpretable machine learning, where I said the opening of that book, if you read it, you will see where they talk about the patient that eventually died. And when this patient died, the medical experts were looking at the results, and she was thinking out loud that if they could have done this and done this, the machine wouldn't have given that person overdose. So understanding what's happening could help you to save life. And then also in the area of economics, you could imagine these days there is a lot of hype around cryptocurrency and also stock market. We could see last time in the US, the stock market crashes because of the decisions of the president, Donald Trump. So it's a sensitive area that has to do with people's investment. So if you don't have a way of understanding when the market is going to crash, although this understanding is shrouded in uncertainty, but that does not mean you could not be able to minimize some of the losses to a large extent. So having a model that is complex, you cannot decode some of these things. And most of the algorithm now that is helping people to trade, most of them are automated and AI is powering most of them. So if you don't have a perfect explanation of what the AI models are doing, you could likely have issues. And by the time you have it, your customers or clients, they wouldn't want to listen to you. They don't want excuses. They want you to tell them exactly why they are losing their assets and money. So you just have to make sure whatever you're doing is something that is very well documented, that you could be able to follow ahead. So Today, one of the things we wanted to do was to provide a practical experience with the tools that helps us to do this interpretability, and also to help the students to be able to apply these methods in order to understand the prediction of the model. So what I hope you could go home with at the end of the class is to understand the differences between the model agnostic and model specific interpretability methods, and also to be able to implement and apply local interpretability techniques to explain individual predictions. If you remember, I talked about the local explanation and the global explanation. When we talk about global, in this case, we are holding all of them as a group. But when we are looking at the local, most times we are trying to understand what is happening, to individuals that the model is predicting, or the samples are, IDs. So if we are looking at these techniques, they do have their strengths and they do have their weaknesses. There are times that, if you remember last time, I talked about that complexity layer, that when you're building this interpretability, it's like you're creating another complex thing. And it doesn't make sense when you want to make complex things simple to have that complexity again built into it. So we'll look at some of this as we proceed. Then another way is, how do you communicate the results of interpretability? So we'll be looking at the breast cancer data set. However, like I said, you forgive me, I didn't do much on it because I just didn't want this thing on SHAP. But notwithstanding, I will give you a very well explained thing next week. I'll take out my time to talk about each of them. So next week when we come, you will have a more robust script for this work. So please, again, I ask your pardon. I normally prepare the lecture material prior to the day, but this week was quite different for me. So, like I always say, you load the packages that you need, and if the package is missing, of course, you use the pep install on a fresh cell to install that particular package. Then another thing I want to make as an emphasis again is that most of these packages, some of them sometimes may not be the name. So, but what you do when you run into an error, you could highlight it and go on your Google search to look for the proper name for that package. Then with that proper name, you could come back and use the pep install on the fresh cell if you are working from Jupyter Notebook. And if you are using the command prompt, you could use it to directly install, but without having to put the hyphen. So having said that, you would just load the package to see which one. So immediately you run that and it goes well, then the next thing is to load the data set. So like I said again, we're just going to look at the breast cancer data set, but next week I will make sure we have other data sets to explore. So you load the data set. So like I always used to say, before you dive into the problem, always try to understand the data set, look at the source where it's coming from, what does the data set means, what kind of problem you are trying to address, what are the variables that have been collected in the data set. So understand this, familiarize yourself with the data set before you jump into modeling. So the data set we are using, of course, is an Scikit-learn data set on breast cancer. And it's actually a data set that has to do with classification, not regression in this case. And then the dataset actually contains measurements from a digitized image of breast cancer mass. So these measurements were used to describe the characteristics of the cell nuclei present in the image. So the features that are in the dataset, it has 30 features, and each of these features are measurements of these digitized images. So the first feature has the radius, which is the mean distance from the points on the parameter. It has the texture. It also have an area, the smoothness, the compactness, then the concavity, concave point, symmetry, fractal dimension, etc. So the target variable is a binary, and another emphasis I want to make, it's binary is a very common thing you'll be seeing in machine learning. but we also have a multi-class, and I think I did talk about multi-class in our previous classes. So we will try to also do the explanation for not just binary. We'll talk about multi-class, so you could have a perfect way of evaluating it. So the target variable 0 actually is malignant breast cancer mass. That's the one that is cancerous. And then 1 is benign, which is the breast mass that is not cancerous. So the first thing you need to do is, like I always used to say, is for you to try to. So remember, when you have the data set, you load the data set. But once you run it, so what we did, we separate the futures and also the target variable. So the next thing is, like I say, you always have to do your EDA, so you familiarize yourself with the futures, the statistics, looked at some of the mean and distribution and percentiles and so on and so forth. So the moment we run that, we could actually see what the first thing I could see, we don't really have any missing values. And yeah, I could actually check if we have any missing, but I don't think so. So I could clearly see we don't have any missing. All of them are complete, and all the data set are float. So which makes a lot of sense. So the next thing, we could just try to do some visuals to see. So we want to look at the distribution of the target variable. Remember, again, I didn't do some stuff I could have tried to color it, but it's fine. So quickly, when you run this, you could see we have more of the okay. So from here, I think we said 0 is the one that has the cancer, then 1 is the one that do not have the cancer. So we could clearly see that the data set is sort of imbalanced. So we have more people that don't have the cancer compared to people that did have the cancer. So the next thing we could do is, meaning they are all continuous variable, we could just have like a heat map of the correlation to see if there are sort of issues that has to do with multicollinearity. Although I did notice some few variables here, but I don't want to dwell more on that because I think we did deal with multicollinearity in our previous classes. But notably, if we are looking at issues that on dimensionality, then we will begin to think of how to remove some features, because we could actually see there is a strong correlation between the mean parameters and the mean smoothness somewhere around here. But we could see, as we keep going, it's not really bad. There is also a bit of something around concavity and also the symmetry errors. Although, like I said, we are not focusing on that today, so we'll be using all the features for the modeling. So immediately, if you run this, so what this is doing, we are just trying to split the data set. And when we put this 0.2 here, we are trying to tell it to split the data set into 80% training and to keep the remaining 20% for testing. And then the random state help us with the reshuffling. So again, I wanted, when I continue developing the script, I'll make sure I include XGBoost, because I don't want us to be used to those random forests alone. There are other interesting modeling algorithms we could use. So I'll look at them subsequently in the next slide. So what we need to do is, before we go into the post-hoc explanation, we need to train the model. So again, remember we did talk about hyperparameter grid search. So you could think about that. Sometimes you don't just jump to the training. You can just have the first train, you see how the performance look like, and then subsequently you could go to the hyperparameter, you could check and see what's happening. So, but today, because the emphasis is more on the interpretability, So I would just make sure we focus more on that so we could use our time judiciously. So let's say we have trained the model, we have also evaluate the model and all that. So the next phase we need to do is to build the explanation. Although I think I did check for the performance, I think accuracy was around 98 thereabouts, so it's actually fine. So we need to start building the post-hoc explanation. So what the SHAP does is to, like I said, it will help us to explain the model either at global level or at individual level. Then, if you remember vividly, yeah, last week I said that the SHAP takes its inspiration from game theory, where each player that is playing in the game, they are all contributing to score the goal. So the each of them from the goalkeeper down to the defenders, down to the midfielders, the wingers, the striker, all of them, the coach that is off the pitch, all of them have to work together as a team in order for them to score that goal. So the glory doesn't necessarily just go to the person that scored it, although that person is very important, but it goes to everyone. For example, if Brazil wins the game, we don't come and say Neymar wins. We are going to say, oh, Brazil wins. If Argentina wins, we don't come and say Messi wins. Won. We say, all of them, as a collective, they all won that game. So that's how SHAP operates on. It takes its inspiration from putting all the strength of all the individual features that are in that particular data set. It combine them and then it model them. But again, another emphasis I want to make, and I believe I did make that emphasis some time back when I was talking with the group of scientists from Bright on the research we were doing, that most of the time people build simple model and then they start building post hoc explanation on them. I said it's wrong because if you are using a model like logistic regression, it's already transparent. So because it's an interpretable model, it's inherently having the interpretation in itself. So why do you have to go about trying to build a SHAP model on top of the logistic regression? It doesn't make sense to me because the SHAP model, the aim is to decode that complexity that is in the model. And we could look at random forest and say, yes, to a large extent, random forest is a black box. But again, when you are looking at the interpretability ranking, random forest is not considered as the very complex interpretability model. Complex black box model. Like I said, in the previous scripts that we'll be developing, you will see where we will get to neural networks, and then we'll see how we interpret it as well. So when you are looking at things like random forest, it did make sense if you do the post-hoc model explanation interpretability on it. But when you are looking at something like linear regression, or you are looking at something like logistic regression, these models are quite interpretable. You don't need to go about building a SHAP around it. So I am always of that opinion that when you have a linear kind of model, inherent interpretable models, just stick to the coefficients or the linear regression coefficients or the parameters in those models to help you to be able to explain whatsoever the model is doing. However, as you begin to move to things, because when you look at random forest in itself, so for example, if I'm doing a decision tree, it doesn't make sense for me to build a SHAP for a decision tree because the decision tree in itself has inherent interpretable properties in it. So just go straight and visualize the trees to see how the splitting is being done. But when you are talking about random forest, where you have so many of these decision trees coming together in some sort of voting approach to combine their strength, then you should need a way to understand what is happening inside that model. Because as you have lots of them, they become a forest. That's why I say it's called random forest, because you are bringing out the strength, combining the strength of these so many decision trees together. So it did make sense when you have that kind of scenario for you to build a SHAP on top of it. So it is on that basis to see we are building the SHAP on top of it. So what the SHAP explainer does is that it takes that model that you have already trained. So for example, this is the model we just fit. So we have fit this model. So we take that model that we have fit, which is this one, and we now build the SHAP explanation around it. So by the time we build the SHAP explanation around the train model, we will now use the SHAP explainer that we have already trained, and then we will use it to evaluate the test result, so the prediction result. So now you see, it's more like you are repeating the process, but in this case, you are explaining what the complex model have already decoded. So now you take the train model from the random forest, wrap it around SHAP explainer, which is in for the training. By the time you do the training, then use that explainer to approximate the predictions. So you see, it makes sense. Now, here is why it makes sense. Because you're pretending you don't know what the model did during the training phase. You don't understand it. And you really want to understand what the model is doing. So in order for you to understand what the model is doing, it did make sense if you could take the model to the theater of SHAP. So the SHAP now will put it in its own ICU. So by the time the SHAP decodes it and diagnose the disease that is wrong, that is the problem that is wrong with the model, then it will take the cure that it has discovered and put it on the prediction or the new arrival. So that's how it kind of works in real life. So just like if you understand, during the pandemic in 2020, you see that for us to be able to solve the COVID puzzle, they have to take the big spike from the virus and then use some RNAs and all that to be able to develop the vaccine. So when the vaccine was developed, so people willingly bring themselves forth for trials, for clinical trials. So after those people first went for the clinical trials, they were monitored for some time. They were able to scale through. Then other people now were now willingly going to receive the vaccine. So that's how the SHAP works. So you first take the training model that you have trained, put it inside SHAP, train it with SHAP, and then explain it with SHAP, then take the explanation you had from the training, apply it to the prediction, because the prediction is where the issue lies. Remember the prediction phase, we don't know what's happening inside the model. So that's where the issue really lies. So in order for us to understand that, we need to take what we have already known, which is the training phase, to be able to now help us to decode that. So that's what this phase does. So it helps us to train it. Then the moment we finish this training in this phase, we now apply it for the testing phase. So once we have applied it, we can check the output of the SHAP, what was fed into it, how many features was fed into it in the testing, how many samples does it have, and then we could build a sort of a summary plot. So the summary plot here is more like a sort of a dot plot that is helping us to visualize what is pushing the prediction forward, what is pushing the prediction backward. So when we talk about forward and backward in this case, we're actually looking at the two classes, the binary classes we have. So remember, the two binary classes is if it is cancerous and when it's not cancerous. So what features are supporting why the patient should be diagnosed that this patient is not cancerous? What features are saying no, it favors the cancerous patient? So it's more like a tug of war. I remember National Youth Service days when in camp during National Youth Service in Nigeria. one of the games they do is called tug of war, where there will be some coppers from this end, another coppers in this end, and then the both of them will be dragging this whole thing, and the person that eventually pull the other group wins. So that's how the SHaP splits the futures around it. So it has to kind of, you know, struggle within themselves to see which of the futures actually outperform the other one, favors the other one. So that's what basically you see this particular phase is doing. So the moment we runs it, it will take a bit of time, but it has run. So the next thing is for us now to look at the futures. So clearly we can actually see that the future that is at the top of our the futures is the worst area, followed by the worst concave point and the worst parameter. So the worst was actually at the top, then followed by the mean of the concave point and the radius. So the next thing we are going to really actually look at is what direction is it pushing towards. So it seems like the lower value of this particular worst areas seems to push the value towards a positive direction. That you can actually see because now this is like a heat map, not even like this is sort of helping us to be able to the C map here help us to understand the density as we're moving forward from the negative to the positive. So we could actually see that the high values of these actually favors the low, while the negative values favor the high. So, but for this particular point, a lot of the patients seems to have high value of it. However, meaning that if we go subsequently in the interpretation, we will see the directionality that this actually favors. Does it favor a patient to stay not to be non-cancerous, or does it favor a patient to be cancerous? But normally, the first 5 futures help us to actually have a proper understanding of which of the futures are most important. Now, if you look at the next future follow from the worst area is the concave point. Again, even in the concave points, we did have some futures, some push towards the positive side, but we could see that majority of the futures seems to favor the green part, the blue part, which is on the positive side. Then the same thing as we continue to go down, we keep seeing there is more push towards this side compared to this side. So we could pick like a first 4 samples or first 5 samples in the data set to see how their direction is moving. You could, if you like, you could pick the first 10. If you like, you could pick the first 2, or you could even pick the first person to see. So let's say we want just one person, for example. Let's pick let me see sample 0 here. Yes. So if you pick the first person or the first patient, you will see we want to see what direction that patient is facing. Now let's look at it. For this patient, there is more it's all positive, of course, looking at the fact that this is the positive and this is going to be the negative. So when we're looking at this, we could see that the first worst area is plus 0.007. The next one is around also plus 0.007, followed by around plus 0.004 and all that. But all across, this patient don't have any blue. And another interesting thing is that when you put up all the density function of this patient, we have around F equals to 0.98. So automatically we see this patient favors the cancerous part. And we could see that the reason why the model is saying this patient is cancerous is because all the areas or all the futures that are at the top for this patient, they all facing the red part of the scale. So we can actually see that, yes, for this patient, this is the reason why it's saying, because the worst area is driving towards the red part on the C map here. The same thing all the features, in fact, for this patient pushes or it favors that red part. But let's say if we take another person on maybe on 10, patient 10, for example, you could see there is a mixture. It's not completely red. There is a mixture of this patient, and also there is a decrease in the density function to around 0.94. And then we could actually see that there are some features that actually favors the blue part of the scale. But we could clearly see also that this patient has more of its future pushing towards the higher part of the scale. So because of that, and also when you look at it, this is 0.94, which is quite a very strong probability distribution, compared to another person. So probably we could try something around 100. Let me see. Aha. So if we take another patient at 100, you could see that the F have reduced. The density function is very small, around 0.07, which actually automatically make this person to favor non-cancerous. So we can see the only thing that is red here is the mean of concavity. But all across for this patient, everything is blue. So because of that, we could say this patient will definitely fall in that category of non-cancerous. But maybe if you take another person, probably around 1 or something, the story will be different. Yeah, so you see, so the more like this one is so high that we have the probability distribution, the density function to be around 0.996, which is quite high. So as you change, so you could see what the SHAP does, it helps you to give you that granular interpretation of each of the sample IDs in your data set. So you could keep searching and checking